Okay, during the aging, telomeres decrease, DNA unstable, and cellular senescence increase, stem cell rejection. Okay, sun tanning may generate DNA breakage and then make the trouble, or others either becoming hungry or intermittent fasting can help to live longer. That's proven. Proclamation, metformin, resveratrol was included in the presentation last time. By one, IGF is the insulin growth factor. Faster growing make faster aging. That's why the bigger dog can live longer than small dog, right? Opposite, right? Small dog lives much longer than the big dogs. There were two main signaling pathways we have learned. One was the growth factor pathways going through or target of rapamycin, and the other pathway was going through the AMPK, which is sensing the nutrients. Those the two are main factors for regulating the aging. Power pathways, if it is activated, goes faster for the aging. Higher nutrient make it faster. Low nutrient make it safe to make it a little longer. Good. Target of rapamycin is the immune suppressant of the raising rapamycin is also proven to make the lifespan longer. And Jagan gave a talk last time and introduced this raising. 재근이가 잘못한 거야. 그래서 메이트도 잘못한 거야. NMN is a regulator for epigenetics. 이런 거 아니야? 한 보니까 다 얘기 잘 했던데. 나중에 뭐가 수 있으면 확인할 거야. Okay, the main reason is for the direction of synthesis of DNA. Okazaki fragment, the phenomena make the full synthesis impossible. That's why telomere getting shorter and shorter. Lifespan may be elongated, and cell division number can be increased, may live longer, and maybe forever because of the dangerous possibility that it can be cancerous, and telomerase may be elongated too. Telomerase is the enzyme which make it of a telomere. And to make a telomere, you need a primer. Very funny way, it's a DNA polymerase, but RNA templated DNA polymerase. So here in this case, they use the telomere, which is not true, sorry. Primer is RNA, the template is also DNA. DNA templated the DNA polymerase, but interestingly, they use RNA, the primer. Okay, there are the two kinds. One is a selective killing of the aged cells, senolytic. The other is changing those aged cells into younger ones. That's a xenomorphic. Those are two different approaches. And then one more time. Element is epigenetic modifier, and that is a precursor of NAD+. NAD is the cofactor for deacetylation, and that's why NMN is provided, so deacetylation, so NMN is provided then that induce deacetylation of the gene, and then DNA demethylation may be opposite way, and gene expression will be decreased. That's the effect of NMN. Well, it's either violet or the red, right? 4 to 6, is that statistically meaningful? Or is it random? Okay, outer of the ring is a red color in rainbow. 관찰력이 좀 우리가 찍히게 되는 I gave you the answer in my lecture. Okay, there's no pure Korean words for green. 녹색 is not Korean, that's a Chinese character. Okay, all others are the electromagnetic wave, and then the sound is a different kind of wave. So, sorry guys, last week I had really serious problem about my voice. So today I came back, and today we are going to learn about the light and color and spectroscopy. Okay, today we are going to learn about the light and reflections. Let's see. When we study about the material, how do we study? Analyze. How do we analyze? light in one way, but let's take an example. Maybe you have heard of this kind of story when you are a primary school student. Now, from now on, I will show you three materials. A, B, C. Okay. So here is the material. A. This is material A. Material B. Material C. So, for this analysis, what did you use?
Sound.
There's a sound. How did you catch it? We use our sense, right? Which sense did we use? Hearing. We have a five sense, you say, except the sixth sense, right? So we have five sense, and if you think about those energy source to reach here, what did you use? What was transferred here? It's a wave. What wave? Here's a sound wave. Sound wave is kind of a wave, but that's different from light energy. Correct? In the last case, we said the two different kinds of a wave, at least in this case. One was sound, and the other one was electromagnetic wave. Now, if you think about our five senses, here, hearing is we use sound, the wave as the medium. Okay? Vision, now it's obvious now. Vision, we use light as the source. How about the other three senses? Taste and smell, what do you think? Taste. What do we use? It's a chemical reaction. At best, biological reaction. If you assume the receptor as a chemical component, it's a chemical sensing. How about the smell? How is it different from smell from taste?
Sensing source.
Say again?
Sensing source.
Sensing source, how different?
States.
States of?
State of it.
What's the difference of those two states? One is a gas and one is a solid. So, solid, gas, none of them we can sense. Our receptor, either nose receptor or mouth receptor, they can sense only solution. If they are pure air or the gas or pure solid, we cannot taste, because that's a molecular interaction, right? To get the molecular interaction, the material should be in the solution. So even though originally the smell is a gas molecule, but reaches to the nose, it should be melted and smeared into the solution, then we can sense. That's why once we have the cold, and then our nose is dry, we cannot smell, right? So basically smell and taste is basically same sensing. Just the location is here and location is here. It's chemical sensing. Leftover thing, touching. This is sensing pressure. The pressure sense is delivered to here. Every sense is come together to the brain, and then those transmittance is a mixture of a chemical reaction and electric signaling coming here. So those are what we are using. All the analytical machines we use is basically the same. All the machines we use, analog or any kind of microscope, anything, the source, if you think, either sound or chemical sensing or using electromagnetic wave. So I showed you the three cases here, ABC. two of them are identical. Which was identical?
Second, third.
Second and third, B and C. Do you agree? A and C, why? This is the C. Did you see the answer? This is the A. And B. This is the D. Still your answer is A and C? Yeah, it was A and C. What's going on here? So all you heard is just a little different sound information, and based on that, you are guessing. Electromagnetic wave may give you a little more defined information. So basically, it's a similar principle. And this is B, chocolate coin. This is the C, metallic coin. And this is the A, metallic coin coated with a tiny plastic bag. And that means, even though it's the same material, how you treat your sample, your result can be quite different. Just a small, the packaging, if you use your eyes using electromagnetic wave, maybe you could say easily, which is identical, maybe super easy, right? Now in this case, you use a different way. Electromagnetic wave will be used for the lenses. Now, maybe extra information, maybe this is shiny. Metallic property, maybe you call, 아는 척 좀 하면, metallic property. Now we can explain why metallic material is shiny like this and things. Anyway, so based on this kind of interactions, mainly we use, if you think about our sensory system, we use wave as a very important source of information and chemical electrical sensing. Now, we said, people say the information we can get from our vision is very high quality of the information. So we have two-dimensional perception and different colors and depth feeling too. So maybe four-dimensional, five-dimensional kind of information we get very fast. Sound transfer 340 meter per second. Light 300,000 kilometers per second. It's a million times faster. Only limitation is the speed of transferring that signal from here to here or here to here. They may be similar. Other than that, information transfer speed is super high. Now, light. What is light? You already have learned about the identity of light. You may have an answer. What is it? What is light, Jenny?
Photons.
Light is composed of photons. Okay. Wave, water wave. What is a wave? Water. Yeah, wave is composed of water, but wave is not water. Light is? Yeah, light is? 하정아, light is? 형부를 왜 지난 시간 안 왔대? What is light? Electromagnetic wave. 수업 누구밖에 안 났는데 빼먹고 그러면 어떡해? 어떡하려고 그래? It's electromagnetic wave we have learned. Exactly whether we understand the character or not, that's a different story. But other scientists, they tried to analyze the light, and it seems like it's electromagnetic wave. Has common speed of light. And regardless of the wavelengths, they travel in the same speed, and no standing mass, but it has an energy, right? So that material, if you call photon as a material, yes, it's composed of something, photon, not tangible. It's a tangible. If we have a light, then it becomes warm, right? We can sense it. It has energy. Anyway, utilizing the light, and we no, No, this is a different one. Okay. So light, one of those the light application we use is a telescope and microscope. Telescope and very far away, very small things we magnify and visualize. Microscope is very small thing, we amplify it and then we visualize it. And we can print it into the same size of a picture. Correct? Then, with a telescope and microscope, it has an opposite principle or it has the same principle. Basically, it's the same principle. Name one is a tele, far away, micro, very small, but basically, very small things make it into visible size to our eyes. That's the two different techniques, right? Then, can we use a telescope instead of a microscope? If it is possible, then why don't we buy separate two machines, right? We buy telescope and then just focus on the microscope, right? Then what's the difference? We assume that we know light. We assume that we are familiar with the telescope and microscope. And what's the difference between telescope and microscope? Volume and dominant, convex or the concave, and that's a part of those components. Then what makes the difference? Telescope also has a concave convex. Microscope also has a similar multiple lenses. So eventually, what makes the difference?
Refraction.
Reflection? Reflection or refraction?
Refraction.
Refraction? Refraction. What is a refraction? Jenny, what is a refraction in Korean? Or in Finnish?
I can tell you.
Now, what is the property of refraction?
More physics thing. Not exactly a physicist.
More scientific things, which can be topic of our class.
It's about the size limit of the thing you can see.
Size limit.
I think I'm getting confused between diffraction and
Yeah, that's about the diffraction.
Okay.
Okay, refraction. What is that in Korean? It's a kultur. It's a refraction. Refraction is in different media. Light has a different speed, so it looks like the curve, the movement. That's a refraction. Okay, in this case, the basic difference between these two is focus, focal distance. Whether we see very far away or focal distance is far away, then that is the telescope. We focus on that object there. Microscope, our focus, we focus this way. If everything is open, if you think about our eye has very small hole. The image is not coming from like this. The image should come from very small hole and then cross and then dispersed and then put on the screen behind here. And that defines those focus. Which one we are going to see? The lens is combined to see the focal or the point is far away, and that's a telescope. Microscope is change that into very small, very near here, then magnify. Those are the main differences. Now, let's think about we said in the study of the material. Chemistry is a molecular science. So material, molecule, let's say. And what kind of interactions we can think out between light and material. Already we have two here. Refraction is one of them. And in different media, light change its speed. Oh, we said the light speed is the same, right? But now I'm saying light speed is different. Who can fix this purpose? Okay, simply speaking, light has the same speed in the same media, regardless of the speed of the observer and object. In different media, light speed can be changed. Okay, so refraction is one way. Diffraction in Korean, what is it? Pleasure. What is diffraction? Jenny, now your turn again. Diffraction is a small thing, and what did you say?
Depends on the wavelength of the light. It's how small of the object you can like make out.
You said something a little blurry or something? At the edge of those material,
Yeah, that's what I said.
a little developed product.
Uh,
You said the wavelength of light. What is the wavelength of light?
well, it depends on the light.
Okay, blue light.
Well, quite bad for seeing things.
In numbers.
400 nanometers.
Okay, 400 nanometer. So blue or violet is a 400 nanometer. So this is wavelength of light. Goes to the red color. Longest wavelength we can see using our eyes. What's the wavelength? About 700. If you are young, I can see only 650. So that sensitivity getting shorter and shorter. So let's just say 650 from my view. So this is the range of the wavelengths which we can see using our eyes, so-called visible light. Okay. Diffraction. Anybody can define diffraction? You haven't heard of diffraction. What is diffraction? Okay, before we go to the details, let's think about other phenomena. If material meets light, what can happen? Absorption. Anything else? Reflection. And Salan in English? Scattering. Anything else? Okay, let's compare reflection and scattering. What is the difference between scattering and reflection? What is reflection? Light hits material. It reflects, right? What does that mean? Reflect.
Based on the angle, the incident angle.
Angle, same angle, incident angle and
It will
outgoing
reflect.
angle is the same way.
Yes.
It's bouncing. That's a reflectors. 반사, same angle and smooth surface, like a metallic surface or the mirror surface. And what is the spectrum?
When it hits the atoms of the material.
Okay, it hits and then
they go off like a random direction.
they go up, not go down.
No, the reflection angle is not controlled. It's not.
You gave the keyword random.
Yes.
Basically, reflection and scattering is the same phenomenon. Reflection and scattering is the same phenomenon. Only difference is reflection is smooth surface, and then everything was coming into the same angle, and then move out in a ordered way. Then that's what we call reflection. If it's irregular surface or small particle, or small hole, and it becomes randomly move out. That's a scattering. Then we combine these two as the same phenomenon. And refraction is a little different. This is just a different speed, just a different phenomena. Now, diffraction. What is a diffraction?
The wave is amplified.
The wave,
It's amplified.
say,
Amplified.
that's resonance. So we have this, the wave, and if we get same frequency of the input, it becomes bigger and bigger. That's resonance. That's a different. Diffraction. So now, what is a diffraction? When do we observe the diffraction? Small. Transmit small forward. Okay. Yes, true. Okay, then let's make it big. We have the wave bladder. So this is seashore. Water wave is coming here. Okay. So we amplify the wavelengths much bigger. Okay, coming here. If this is a very big hole, they just pass through. If it becomes smaller and small, now there's a chance that they becomes diffract. If it becomes very small, yes, it becomes almost every reactions, they change its pathways. And if it's much smaller than this water wave, there is no effect. It doesn't pass through. Now, diffraction is maximized. Diffraction is when it meets any obstacle or hole. It is maximized to change its path when the wavelength is close to the gap. That means that when it is a very small hole, that experiment is a Young's interference experiment. In the case, wavelength of light is very small in our scale. That's why they try to make it really small, the hole, using maybe razor. Still, that's much bigger than this, maybe. Still, that's closer to that range. Then we started to see the different paths. And then if you have two of them, then they generate sometimes summing up, sometimes subtracting, generating interference. Okay? That is resulted from diffraction. Now, my point is, diffraction is also changing its pathways by interacting with something here. That something is, in this case, if you think, reflection, photon comes in, hit, and then move out. Which material interacted with the photon, do you think?
Electron.
Second?
Electron.
That's electron. Material is composed of nucleus and electron. Whether the photon interacted with the nucleus, no way. It's interaction between electron and photons. Reflection, scattering, both cases, the interaction is electromagnetic wave and electrons interaction. And they change its pathways randomly, or ordered way, or angled way. So this is also same phenomenon. Just showing a little different way, but basically these are all summed up, as you can say, scattering. When material meets light, one phenomena is a scattering. Interaction between electron and electromagnetic wave. Electromagnetic wave is a plus minus moving. And electron shell is always a negative charge. Minus comes in, they push it out, plus comes in, they are attractive, and no stop. It's just a pass by, but it's just changing its pathways. That's a spectrum. Ordered way, we call it reflection. Random way, scattering. And patterned way, diffraction. That's one phenomenon. Another second phenomenon is absorption. Light comes in, meet material, and that photon is disappeared. And that energy is transferred to the material. That's absorption. That's why we feel warm. Means that the sunlight energy is absorbed into our body. That's absorption. So two major phenomena. There's one more we're going to talk later. So if you think about the interaction of light and material, very basically, you can sum it up. Whatever the phenomena you call, basically it's two things. Or one more thing I'm going to talk later, and that's the interaction you can think. Then those study about the interaction between light and material. Can you guess what you call? Optics. When you say optics, pass through the lens and whatever, those are what you call optics. Then what is spectroscopy? Then what's the difference between optics and spectroscopy? You guys have heard many times spectroscopy. In Korean, 분광학. 분광학, 분 means divide, 광 means light. So divide light. Spectroscopy has that kind of meaning. Here, the spectroscopy, I tried to ask you some of those terms. Scopy is a seeing. Spectrum means it's coming from a spectrum. That spectrum is some band of from what we can see, 400 nanometer to 650 nanometer range of continuous color changes bundle. This was defined in the beginning spectrum. It's kind of a bundle of light covering all the colors we can see. Where do you see that color? That color is basically perception, utilizing our other senses, and then you can see this range. And those colors originally we found from nature, like rainbow, and then we realized there is a various of the color ranges, and then in the beginning we defined that a whole collection of different colors as a spectrum. Now we use it very metaphorical way with the spectrum of a political opinion. Kind of a different meaning we use, but original the meaning of a spectrum is whole range of diversity in terms of the colors. And then our eye has 3 receptors, and not continuously covering every color. And here, when I ask chemically, physically, psychologically, how can you generate LSD? Anyway, color perception is illusion. This is just a different wavelengths of the light source. Just we interpret that into colors to maximize those signals. And yes, illusion is one way, but if you look at those, it is physical, the color sensing. Now this is the RGB we have. If somebody designed our body, RGB. If you make color screen, okay, in the video, the clip, I gave you the dog's view or color blind people's view. If you have one of them is broken, then you have only 2 sensors. Then the combination power, as we learned in antibody generations, is a 2 combination. You can see only 100 colors, they say. With just one more, the color sensing, the combination becomes a 3-dimensional. Almost we can see 10,000 different colors we can distinguish. Now, seems like dogs and cows, they have only one combined one here. And if you design the RGB much better means to present different colors. Maybe you wanted to put R, R, G, B, maybe in the same interval. Then you can get more diversity. If it's very close like this, then the diversity is narrowed down. Then we can assume that originally we had one receptor. And one time, maybe one of them has a mutation, and it's shipped out a little, and then divided a little like this. That's why majority of those animals, they have a two-color system. We have a three-color, but not perfect. Maybe that's the history in this case. Now, RGB sensors, yeah, maybe some mutations can happen, and in this case, what do you say? Even this mutation happens one more time, we have three colors, but those mutations happens again, and then a little further the deviation, and we have a three-color trichromic, we say. Sometimes some people say it has tetrachromic. Usually males compared to females is simpler and has a more defect, so most of those colorblind happens to males. Right? Female has a 2X chromosome, and they have more chances to have recover or make another mutation. So some people may have four color system, tetrachromic. Some artists, exactly, we do not understand how the color looks like to her, but some maybe more various colors could be seen to them. Very funny way, the gambunga, the goldfish, we say they have only 3-second memory, stupid. But interestingly, the goldfish has a 4-color system. They see the world much more brighter or more diverse than we do. Anyway, using these kinds of systems, another way of the making color, maybe metamaterial is kind of removing the older colors. Another case I want to be here was transition metal complex is the way to make the colors. So those absorption, light absorption, as we have seen here. So this much of those absorption is covering one part of the visible light. Then only the other part can be seen. So we have studied about conjugation system changes, particle box changes. That's one way. Organic way. Inorganic way is utilizing this transition metal, and they have p electrons. Those electron values are near to visible light ranges. So once they absorb that light, they look like the color. So those are two chemistry-wise or material-wise, two ways. It's not LSD. Okay? LSD effect may be different to different people. It's not the consistent. Right? So common way is we use transition metal way or organic material way by changing those signs. Now, from white light, definition of the color was not easy even to Newton. So he proposed something. White light is the basic material, and some component is added to make the color. That was his suggestion. But from now we know that white light combines everything. And then it can be divided into different light sources. Everything is combined together. That's what we call white light. And that's most abundant light in our life. That's why we suppress the signal as a background. That's why we sense that as a white light is artificially defined. So natural, the source of the spectrum is rainbow. Here's one example I showed you. Outside is red color. So some people say it's not rain. Well, if you look at a little bigger angle, then it looks like the really ring. Right? Outside is red, inside is blue. Blue is shorter wavelengths. So let me test your observation ability. Inside and outside of the rainbow, which side is brighter? What? Inside is brighter? Why? Let's check first of all whether that's really true or not. Which is inside? This is inside, right? This is outside. Yeah, inside is brighter. Interval. Why inside is brighter? Yeah, very funny way. Rainbow inside is always brighter than outside, whether you recognize it or not. Inside is always brighter than outside. Inside, outside. Now, the mechanism of making rainbow is similar to prism. There is reflection and dispersion, different angle of refraction, and then they disperse with light. That's why those position of the rainbow is defined by the angle. That's why even though we go close to the rainbow, they move back, right? Because to keep this angle same. Then, if that angle happens 2 times of a reflection, then this is a regular rainbow. But if it happens 1 more time, and then with a higher angle, it can form double rainbow. In double rainbow, one was inner circle is primary rainbow, outside is a secondary rainbow. If it's a double reflection happens, the order of color, inner one was from blue to red, right? Outside was red, right? What do you think for the second rainbow? Opposite means? This is the first rainbow. Second rainbow, that's what Henry says. If it's 1 reflection, this is a 2 reflection. That's true. Red and blue. Now let me ask you a question again. Now you have the three area. 1, 2, 3 area. Which area is the brightest? Which one is the second brightest? Which one is the third brightest? This was brightest part, right? In the blue side. Then this blue side may be second one. And this may be third one. 1, 2, 3. We don't have much time, so it's the homework. Explain why. I had one more other story to tell you here, but we don't have enough time, so we move in to the next one. So IR, if you read it IR to the material, what happens? If you take IR spectrum, what happens? Absorption happens. Utilizing those absorption phenomena, you measure those different vibration or the rotation, anything you see. And photon of red light, wavelength of a photon is 650, we said, right? And what size of a photon is it? There is a wave of water, and usually they'll compare this wave as the water is composed of water molecule. The photon is like a water molecule, and this is the wave. Usually they use this as a kind of an explanation. That's actually quite a bad explanation. This photon, even a single photon, you have heard that if they go through sleep, they can diffract and they can interfere. Then reasonable, the picture of this is photon size may be similar to wavelengths or half of the wavelengths if the wavelength is like this. This is 650, then maybe half of this should be maybe 300 nanometer. that may be more reasonable picture rather than we assume that the photon is very small. Now, if you think about the molecule size, what is the size of the molecule? Even though with a long conjugation. One bond is 1.5 angstrom. If they connected together 10 atoms, it's about 1 nanometer. Now, one molecule absorbs one light. 1 nanometer size absorbs much bigger light, something like this. Even this is a molecule, even maybe this is a more realistic. This is a molecule, and this is a 1 photon size. This may be more realistic picture. We think about absorption. Light is much bigger. Photon is much bigger. 100 nanometer size, and material molecule size is very small, and that is absorbed into this material. So I just said about the absorption part. So if you look at the bacteria, just a simple white light, and sometimes we cannot recognize those. But actually there are two kinds of bacteria at least, utilizing gram reagent, gram positive and gram negative. This black one, the purple one, is gram positive, and then the pink one is a gram negative one. If it is stained by this purple one, crystal violet, then they are called as gram positive. We have learned before. Okay? And then there was some questions. Why do the gram negative bacteria look pink? Is there any other staining? Yes, it is also stained. So this purple one is crystal violet, and then this pink one is a saffron. Saffronin is pinky and it stains all the bacteria, but that pink color is covered by this strong purple one. That's why it doesn't look like pink. So two reagents has been used. One reagent, weaker one, stains them all, and then positive one stains only the positive. Now, this picture is made by absorption. Okay, only some color is left over, and this is no absorption happens. So this is absorbed maybe. Purple color means maybe green color is removed. Green color is absorbed. That's why blue and red color is removed here. Okay. So past this, now we this is discussed about the interaction in terms of scattering is one way, absorption is the other way. There's one more the phenomena which is explained by Levin. Will explain about this phenomena.
So hi, my name is Yubin Kim, and I'm going to talk about fluorescence today. And I really wanted to cover the real basics of fluorescence, so it's really simple and short. So I hope most of you would understand after this presentation. So let's start with the question. What is fluorescence? I think most of you know what the highlighter is, but why is the highlighter called 형광펜 in Korean? What is the difference with the normal pen? So to answer this question, we need to know about light absorption and fluorescence. The normal colors, just like the image printed on the paper, they absorb the light. If we see the printer, we use 4 inks: cyan, magenta, yellow, and black. Molecules in the cyan ink absorbs the cyan light beside the cyan and reflect the cyan, and that light enters our eye. So that's why cyan ink is colored cyan. Then where did the absorbed energy go? The molecule absorbed the light, and did the energy just disappear? Of course not. The energy is converted and consumed as heat, vibration, or any other way. This is how color is generated by absorption. The molecule absorbs light. We can see the light that isn't absorbed. The energy absorbed by molecules is consumed in various ways. Then would it be possible for the absorbed energy to be consumed as light. That's the key point of fluorescence. The molecules absorb the light and the electron is excited. The electron may emit light and become stable. This light, this phenomenon, is called fluorescence. There could be further stabilization process. So the energy of fluorescence light is always the same or less than the energy that is absorbed. To sum up, the color generated by fluorescence is a color from the emission of light after the molecule absorbs the light. Let's examine the Jablonski diagram. Jablonski diagram illustrates the electronic states and often the vibrational levels of a molecule. And there is a phosphorescence in the diagram, but it's not covered in this presentation, so please ignore it. So as we can see from the diagram, in case of absorption, the molecule absorbs the energy and it is stabilized with vibration or other ways. We can see the unabsorbed light. In the case of fluorescence, the molecule absorbs energy and emits the portion of the light. The electron can be stabilized further with another additional stabilization step. One example of fluorescence molecule is this molecule. I thought many of you have listened to the course named 1화학실험 2, and this is the molecule that was used in experiment 7 at that course. The name of this molecule is fluorescein, and this molecule has a peak excitation at 495 nanometers and 520 nanometers emission. It's kind of green light. So why do we need to use fluorescent dye? Let's assume that we need to dye certain types of mouse eyes with an orange dye. It's not fluorescent, it's just normal dye. So there's lots of mice, and some of the mice are dyed. Can you count them? So I don't know if you count them, but yeah, 4 of them are dyed. So I think it took some time to count them, right? So let's turn off the light. Can you find the dyed mouse? Absolutely not. And how about now? Fluorescence is much easier to be observed at a glance. It's the same as single candlelight in the dark, and it's much easier to be seen. We can use fluorescence to detect a few molecules or particles because of this. Also, we can see fluorescent light in dark conditions, so that's also a good advantage of fluorescence. I heard someone questioned why we use fluorescent dyes rather than normal dyes in previous class, so this is the reason why. This is an image of cells dyed with fluorescent dyes. It's a type of human cancer cells on the left and endothelial cells on the right. The cell is dyed with several fluorescent dyes depending on what we want to observe and image, and that image is overlapped right here. So as you can see, the background of the image is dark and you can observe them much easier. There are many other examples of fluorescent dyed materials, and you can find them very easily. So this is all what I wanted to talk about. And is there any questions?
Okay, questions?
Okay. Thank you for presenting. And I heard that fluorescence is a very good technique and many diversity. And is there any library that we can categorize fluorescence? How can we define this fluorescence?
I didn't understand the question. So, what do you mean by categorized fluorescence?
I mean, fluorescence that you could see like fluorescing or another fluorescence, and how can we divide the fluorescence to
우리말로 얘기해 볼래? 질문이 뭐야?
죄송합니다. 그 형광을 많은 형광 물질들을 볼 수 있는데 그거를 분류할 수 있는 기준이 있거나 분류한다면 어떤 식으로 분류할 수 있는지.
Well, there are different kinds of fluorescence molecules. Maybe one way of classifying those molecules can be depending on their colors. And their colors can be defined in two ways. One is, this is the absorption method. First step is absorption. So absorbed light can be dispersed by the thermal energy. So we have the sunlight and all warm. Our hand does not shine. So this energy is dispatched by thermal energy, then it's not fluorescent. So that's the color you see. If you see this color, so this color looks like a pink color. Okay. This color is defined by this absorption. And some light is removed by this absorption, and that light is observed in this two molecule. That defines the color without any other under white light. And the emission color is defined by this energy gap. Observed energy is not fully dispatched. It's partially removed and then restabilized here, and then they come out. So depending on those energy gap, they have a different wavelengths. So let me show you an example. This is the pink color. This is the pink color, right? But if I read it with the light, this is the fluorescence color. What's the difference? So actually, pink is not in the rainbow color, correct? That's not wavelength defined the color. Pink is how to make a pink when you mix the different the ink. White plus red, right? That means pink color is defined by pink color in Korean 분홍색. 분 means powder. You add the white powder into the red color. So this is mixed with the white color with the red color. So this is the defined by absorption. And then just what I showed you was orange color. Orange is a part of the rainbow color. That's defined by the wavelength. So if you classify those molecules, that can be defined by how much of energy can be absorbed, how much energy can be emitted. So altogether, today I said, if there's any interaction between material and light, one way is the scattering. Passes through, but somehow affected. You guys have learned about the optical activity. That's also a part of the scattering, moving this way or this way. And reflection, the diffraction, all kinds of those phenomena is belonging to the scattering. The other kinds is absorption. Most of those absorption just dispatch those energies, just released by heat. That's why we don't see emission. But some part of that absorbed light can re-emit. So this emission is different from scattering. This is observed and keep those energy for some time, and then re-emit. Those time delay, sometimes nanoseconds, or microseconds, or milliseconds. Depending on those time, we can see those energies in a different time domain. So these three are main interactions between light and materials. So one of those techniques, which one we look at, is defining the different techniques. X-ray diffraction and UV visible absorption, IR absorption, NMR spectroscopy is a part of emission spectrum, and fluorescence, and this is also emission, but this one energy source is not light. This one is energy source is electricity. So this emission we call electro emission or electroluminescence. Okay. But all the phenomena is involving this electronic transition. That energy is stored in the material in terms of electron jumping. And then that energy is re-emitted. Those three are all covering all the interactions. So whenever from now on you see any kind of a spectroscopy technique. Spectroscopy means light and material interaction, but using specific wavelengths. Out of a spectrum, using one wavelength, either UV, IR, visible, microwave, X-ray, whatever the light source. You choose one wavelength and then interaction with the material. That's a spectroscopy. That's why it is very broad and many techniques are there. But if you think about the key definition of the spectroscopy, whatever technique you hear, you think first, is that absorption? Or is that fluorescence? Or is that emission? Okay. Gluconolid, if you have some material and with the fire it goes up and generates some colors, is that emission or absorption? That's emission. That's a specified color, and large energy is observed, and then that electron jump up, and then there is re-emitting the color. That's why different element has a different specific colors. That's a kind of emission. Just the absorption source is different. Okay, so I tried to compare you very basic or very general the property of light and the materials interaction. And next week we are going to look at a little more specific example for biological the applications of these floating materials. Okay, any question? First of all, thank you for the video. Any question?
So the explanation,
Sugun.
the thing that we see when there are lights, and it's the absorbed light and emitted light comes to our eyes and we can see it. But when we don't have light, then fluorescence light comes to our eyes. So my question is, what kind of material can fluorescence lights and what kind of materials cannot?
If the material can observe the light, then it becomes colorful materials. Whether this is a fluorescent or not, is that this observed light, observed energy, can be re-emitted as a light or not. That defines fluorescent or not. So that means fluorescence material is a small class. Dye material is much bigger class. So if anything observed, then look at the red color of the chair. Those are the dye material, colorful material. But it's not fluorescent. So colorful material, to visualize it as Yubin said, if you turn off the light, there is no comparison. Only when it has a white light, then you have a reference to compare. Some light is observed, that's why you see this leftover color. So if your background is white, as I showed you in ground positive, ground negative picture, background was white. That means you need to have the light. But in fluorescence case, and that means there's no visible light, but that does not mean that there is no light. Here, UV is irradiated. Just our eyes cannot catch it. That's why the background looks like dark. And then we emitted light shows this energy to our eyes. That means here we needed to compare input and output ratio. If the ratio is less than 10%, now it becomes very dim. Whether it's that signal or not, if you look at this picture, is it yellow or not? If you look closely, even worse. And then its size is smaller, now diffraction happens. And whether there is a color or not, that's getting more and more difficult. So that's why there is some sensitivity issue here. But if in this case, if we turn off the light, if there is a single molecule there, still we can see. In that sense, fluorescence has its own advantages in terms of the sensitivity. Okay, other question?
I have one. You said that when we are facing the light of sun, we can feel the warmth. So is the warmth is the energy of lights or the hot energy?
The energy is observed. The skin has a color. Inside this skin we have a blood. Blood has a red color. Red color means it observed the green and blue light. And then they observe the light. They are not fluorescent, and they converted that energy into heat. That's why only one. Okay, very good. See you next week. Bye.